right, everyone, let's get started. I'll close this out so we can just start a new file. So open up PSoC Creator. Click yes. Ignore this license registration. Let's create a new project. There's a small button right here. You see my cursor, right? There you go. And today we're going to be working with a dev kit, this guy, and quality sucks. Anyway, it's like the CY8C. Okay, that's useless.
Dev kit 46.
Yeah, dev kit 46.
From the box like this, we have a couple of them. We're ordering more. It's simply just the PSoC processor with a built-in breakout board and a couple extra things like LEDs and buttons.
So since we're working with that, we're gonna select that, and oh yeah, right here you want PSoC 4. Sorry about that. So click the drop down, and then at the bottom it says device selector. You're gonna navigate there, and then you're gonna click series. This is a filter. Uncheck the select all, and then check the PSoC 4200L. There's gonna be a checkbox that says 4200L. So after we check that, we click anywhere on the screen. And now we're gonna find a specific one. Okay, you're gonna want to find the option on the far left that says 248BZI-L489 for the last few letters. So find L489 first, and then make sure the 5 characters before L489 are 248BZI. I guess that's 6 characters, but 248BZI-L489. Yeah. Okay, I hope everyone has that. Let me know if you don't. We're just gonna hit, double click it, and then you can click next. Yeah. We're gonna start from scratch, so click empty schematic. This is just a directory you want to put it. You can put it anywhere. Try to remember where you put it. I put it in like documents / PSoC creator.
Don't explain what a workspace is.
Yeah. Workspace is just like a PSoC thingy where you can put a bunch of projects in. But if you're uploading to GitHub, which you probably will for most of your projects, you usually just want one project in your workspace. It's kind of annoying, but yeah, that's how it is.
The main way that we'd use, so a project is basically a collection of files and data that you're using for one instance of uploading to the board. The workspace is useful for like version history of it. So like if you make the V1 of your board, then in the same workspace, you could then iterate and make the V2 just to make it simple and in the same space. But you wouldn't put like different projects in the same workspace because then it gets confusing when you're trying to manage the like the file repositories in GitHub.
Is everyone here?
Is anyone not here?
No one says no. You'll only
Right,
say
you have
yes.
to ask, yeah, exactly.
This is the top design. We're gonna put things that we call blocks, and blocks are just they're used for like common devices or like configurations like PWM. A lot of things, like if you take 474, when you set up like PWM in like a timer counter block or whatever, you're just like flipping registers. But PSoC makes it easier. They just give you a bunch of checkboxes after clicking on a block or a block. You can like edit the settings like visually. So first we're gonna add we can add like a UART block. So on the right side, search UART, and then click the one that says SCB mode. You can drag it over and plop it. And the first thing we're gonna do with UART is we're gonna double click it, and we're gonna name it just UART. without the _1, because it's annoying. I think with these blocks is in the bottom left, after double clicking, there's gonna be a data like a data sheet link, and you can just click on that and you can view everything about this device and the API associated with it. Because when you drag a new block in, you're actually like importing a library after hitting build, which we'll do in a moment. And that's how you interact with it. Okay, since we're using the L489, and it has like a micro USB cable with like built-in UART functionality, we're gonna look at the data sheet for it to find like what pins we need to assign to get UART working through that. So I believe I have a link here. You guys don't need to see this, but I'll just show you like what you would do, which is Google the kit name and then like download user manual. And then you can usually I just use Control F and I search UART or something.
It was an easier way to do it. For some things, but yeah.
I think Bridge will bring us there. Yeah, right here. See that your RX is assigned to 3.1 and your TX is assigned to 3.0. So over here, there's a pins tab on the left. And double click that. And you're brought to this page. And now we're going to assign those pins that we just saw. So you can give RX 3.0. Everyone see this? And TX, we're going to give 3.1. You're good. I guess we can add the CAN block next. So go back to top design by clicking the top design file up here. Just double click it. And we're going to use a search on the right again. Just search CAN. Then we're going to take the CAN controller macro. This guy. It doesn't really matter which pins we assign right now, right?
No.
Yeah.
Stubby pen.
Because we're on the dev board, doesn't really matter which pins you assign to. But normally, you would look at the schematic for the board you're working on. Yeah, assuming I can just click on any project. Yeah, if you go to Altium 365, you can look at the schematic, and you'll see that, like down here, there's a CAN TX, CAN RX. So you would link those pins accordingly. This is like P41, P40 here. Yeah, we don't have to worry about that today. All right, now let's start on the C code. Before we do anything, well, first go to main.c. Should be in source files down here on the left. And we're gonna hit build because we want to use the API calls from the blocks that we just put on the board. So build is this, I can't zoom in, but it's this top button in the left, top left, like the leftmost button. Yeah, it's like two arrows pointing down. So go back to top design actually. Yeah, we have to configure the CAN. While we're at it, let's rename it CAN instead of CAN_1. The CAN operates on an external clock, but we just have this, so we're not gonna connect it to an external clock. But normally when you're programming for the board and it's already on the rover, you want to set up the external clock. Today we're just gonna use the internal one. So go to the, sorry, I'm going too fast. Go to the clocks little section on the left, just double click it, and then double click anywhere on the screen that's yellow. I don't remember what to do here.
Go to low frequency clocks.
Yeah. Low frequency clocks.
Tick the box for WCO.
Oh, up here.
Go back to high frequency clocks. And then under trim width on IMO, set WCO as the trim function. And now you'll notice the accuracy drops to 0.2% plus or minus as opposed to 2%, which will make CAN stop complaining. And then just hit OK.
All right, I'm gonna hit OK. Let me know if I need more time. Head back to top design and double click on the CAN. And we're gonna go back to the timing tab. This time we're just gonna you can set this to 125. This doesn't really matter today, but yeah, usually you have on 125. And then just double click any of these options that appear below. Like any of them. And then click apply OK. Yeah.
Where's that rate mean? Like the 125 rate?
It's the baud rate. It's like, you want to explain that?
Well, it's the data rate of the line. So basically, you can have any implementation. It's just based off of like how fast the clock signal for CAN is running. So ours on the rover is running at 125 because that's the default. So we're just matching with software.
I'll send you guys a ClickUp link later. But in ClickUp, there's a page called setting up the clocks. Oh, sorry, 10 block settings. And it's all the settings we use. So yeah, I'll just walk you through it. On the first page, yeah, okay, I'm gonna move it somewhere. So make sure you're in general for the CAN block. Okay. We're on round robin automatic R2D big endian, which is default. Timing we already covered. Go to the interrupts tab and uncheck the bus off state. Just match whatever's here. Actually, we want advanced interrupt configuration. Yeah. Just match what's on this page. All right, now go to the receive buffers tab. And check the first four and the IRQ. So IRQ and basic. This. I forgot what these were, by the way.
Okay, so what you're setting up here is that in our CAN system, we have a library of files you'd also import into your board. We won't worry about that today. Where basically, instead of having to worry about like constantly checking all the mailboxes or handling all the bits, our library handles all that. If you set this up correctly, what will happen is every time a message is sent to those mailboxes are basically registers or I guess registers are the correct name. It'll just store it there, and then you can access it easily using one of our API calls to the CAN library. So basically, this means it can store 4 messages at a time, and then the interrupt is handling, okay, as soon as it's received a message, it's going to store it to a register as opposed to just like waiting and not doing anything with it. So you don't have to constantly pull the CAN line to make sure you're not missing a message. You just wait for it to find one. In the background, the CAN library will handle it, throw it into a mailbox, and then you can just read it off with an API call.
And the last one we're going to configure is the transmit buffers.
Buffer is the word I was looking for. It's not a register, it's a buffer.
Oh no. Okay, okay. Okay, transmit is default. Yeah. While you're waiting, you can hit build again because we just made some changes. Every time you make changes, basically.
So you need to set the intro. So go to intro first, and then
yeah, we can start getting into C code. We're just gonna play with UART. So whenever you have a block, you usually have to initialize that thing. And you can find all the initialization functions in the data sheet by double clicking and then the bottom left. So for UART,
if you're on the left side, you can go to the menu on the bottom. UART, drop down UART APIs. It'll take you straight to all the functions.
Okay.
Or if you just want to go straight there, it's page 149.
So what we're looking for is start. You just basically replace whatever you named your UART with SCB, or sorry, you replace SCB with whatever you named. So we're gonna do UART underscore start. And we're gonna do that. Oh, sorry. We're gonna do that before the infinite for loop. This is the infinite for loop. It's just for with no conditions. So right before that, we're gonna say UART start semicolon. Yeah. All right, so back to the data sheet. You can see there's a put string function here. And you can like put a string in the transmit buffer. And we're gonna use that to show an output when we connect this. So in your for loop, we're gonna use that. So the UART underscore UART put string. And in the parentheses, we'll put a string, put whatever you want. Let's do hello. And then we'll put a new line character, which is the \n, kind of like in Java. And then you can put a carriage return, which I learned today, which is also \r. So \n, is this a backslash or a forward slash? I don't remember. What do you call it? Anyway, this whack. Okay, whack n, whack r.
Yep.
You guys learn whack.
I always say whack.
Okay, it's whack n, whack r. It's a special character.
Yeah.
So when you put whack n, it makes it a new line. So it makes your text go to the next line. And then whack r makes it slide to the left. So it always sticks to the left. Okay.
Does that make sense? The difference between them. It's only slightly important. Like if you're familiar with any other language for printing, it's like print or println. To println, you do whack n, whack r. But if you wanted to do something a little more advanced, you could just use one or the other depending on what you're trying to do. Like if you wanted to keep rewriting the same line of text in the console, you could do whack r, just return without going to a new line, and then you could write over it. Or you can do just a new line if you want to like make a cascading text or something as you like go over, go down, go over, go down. Not super important though, it's just for debugging.
While we're here, we can add a delay. Like side delay. Yeah. So this is a delay in milliseconds. It's a blocking delay. So basically it just stops your microcontroller from doing anything for 500 milliseconds or however many milliseconds you put in the parentheses. That's just so the hellos don't go too fast. All right, I'll go backwards a little and I'm gonna import two libraries that are pretty useful. So one of them is this guy. Just do #include stdint.h with the two like these things, bracket things. What are those called?
Brackets.
Brackets. And this, yeah, this gives you more integer types like uint underscore 8. Oh, wait, uint 8 underscore t. Right. Yeah. Right. And these guys are useful because the default integer size actually varies across different microprocessors and languages. But if you use this package, it'll keep it consistent. Or I shouldn't say languages, just like different microprocessors, basically. Yeah. So when you type uint 8, it means unsigned integer of 8 bits. So you know for sure that's 8 bits. You don't want to like look up what size an integer is in your microprocessor. And you can just use this library and you'll be sure. And the other library we're gonna include is stdlibrary.h. So stdlib.h. The same sharp brackets. Yeah, that gives you a lot of quality of life functions. My favorite one is IT0 or ITOA, which is like integer to array. It just converts an integer to a string for you. Which is useful because a lot of sensors will, you just like take an integer data from it. And then you want to print it out to UART, but UART doesn't like it. You just put the integer in. So I use ITOA. I guess I can explain how that works. You put the integer that you want, like let's say 34, and then you put a char buffer because it's gonna copy the data to a array of chars. Because in C, a string is just an array of chars. So we can make some. This guy. And then ITOA takes 3 parameters. The third one is base. We want it in base 10 because 34. We want it to print out 34, not something we can't understand. Yeah. All right, that's kind of like a side note. You don't. You'll probably forget that, but it's okay. All right, at this stage, we can actually connect our guy. Find my old code. Oh yeah, hit build once you're done coding. Whenever you make a change, you hit build. Oh, build succeeded. Probably good. As I said before, we're just going to use this micro B cable. I say micro USB cable, and just plug it into any port on your laptop that fits. And then on PSoC Creator, after you hit build, you're gonna see this program button. It's near the build button, but a little to the right. And that's what you're gonna use to program. You guys don't have boards, so don't click it. Yeah, nothing will happen. All right, should I go over the? Okay, sometimes you'll have to open the PSoC programmer, which is an application that was installed on your computer when you installed PSoC. It looks like that.
Okay, so basically, not all of our boards, in fact, none of our boards have USB cables. So the way that we program our actual boards is using something called a JTAG header. So it's like directly interfaced with the memory of the PSoC. That's not important. What's important is it uses this doohickey, plug this part of the board, and then we plug this in your computer. You'll need to open this up to make sure it's correctly connected.
So what is your version of 3.29.0?
That's fine.
That's fine. It's just as long as you have the software. It comes with PSoC Creator. It's just if you're using one of these to interface with a mini Prog 4, you'll sometimes need to configure it in the software.
And it won't let you program if this programmer is open. So after you're done configuring it, just close it out. Usually you'll just have to double click something in the port selection. And then you might want to like change the voltage and click power cycle, or toggle power. Yeah, we don't have to do that with the dev kit usually. All right, so I'm gonna hit program. You guys, it won't do anything. You hit program. And now we're gonna use a tool to read our UART output. So you guys can install something called Tera Term. I can go to. I'm not used to it. Yeah, this guy called Tera Term, which like reads your USB serial stuff. Page looks sketchy, but
it's just old. It's an open source project, so it's not like what we take. Go to download page. But we just want to throw that into Discord. But it's just the exe you want. So then click on that. We should open up to install. Once it's done.
Again, you guys can't really follow along here because you don't have this guy, but you can just click the same things I'm clicking. You won't have an output, but yeah, you can at least try to internalize how to do it. We'll probably pass this around later.
Yeah, we can pass it around if you guys want to test out the program that you write, if you do anything other than, I mean, even if you don't want to test the tutorial program, but we only have one of the boards that we can hook up, unless someone else has a mini USB, then we do have one more, but we don't have the cable for it. But we do have 5 more in order, so this won't be an issue as soon as we actually start trying to test code.
Is the cable not in the box?
Okay, my bad. We actually have 2 of them. So we'll pass those around after we go through the tutorial if you guys want to test the code out and see if it works.
All right, when you open Tera Term, you'll see this window. And every time it's going to be like up here, but you want to click serial. And then port, you'll see like a drop down. You want to find the one that says KitProg USB UART. You can click OK. Oh, we already have some output. You can see this output is like kind of gibberish right now. Like we had some good stuff and then gibberish. It's because the baud rate is different. So we want to tell Tera Term what baud rate we're using. And if you head over to top design and double click UART, you can see that baud rate is listed right here and it's 115,200. So you want to set that value in Tera Term by going to setup, serial port. And right here you select the same number. And then you can hit new setting. And now you see we have a nice hello going down forever. Here's it's kind of dark. Well, here's an example. This is Davis's code for like the IMU, like motor unit. It's just a good simple example of a finite state machine. We use the switch statement. The switch statement takes one input. Here he takes in the variable state. It's probably like an integer or something. Yeah. And then you write case. You can see that there's several case statements. He only has 2. And basically it's kind of like an if statement, and it's saying if this input equals whatever's in case, then you run this case. Right? You run it and then you break here. And break will exit the entire thing. If you don't have break, then it'll keep checking the other cases. Well, that doesn't really make sense because you already checked if this case.
It can have some memory overflow issues where if you don't break, it might just ignore the case for the next one, and then it will just start executing code regardless of whether it should be in the case. So you do want to add a break even though it won't throw an error.
Yeah. You can also have a default case. He doesn't have one here, but you just write default : and then some code, and it'll run that code whenever it doesn't match any of these cases. Yeah. So he also updates the case here. See here he says, oh, the state should be read sensors. So next time it goes through this, next time you enter this for loop, basically, it'll go to this case, read sensors. And then it'll do all the reading sensors, like some accelerometers and stuff and gyroscopes. And then when it's done reading all the sensors, you can see here it switches the state back to idle. So then the next time it enters the for loop, it'll go back to the case idle. And idle, it just pulls for a CAN packet, reads it, sees if if it wants sensor data or something. And if it does, then it'll update the state accordingly. Yep. That's pretty useful. It's just a nice way of organizing. You can technically do all of this with just if statements, but the switch case makes it like very organized. And sometimes you'll have a lot of cases.
Call back to the presentation before. Okay. So if you were planning out the code for this, here'd be like your basic state diagram that you could then turn into pseudocode in this case state. So you have the idle state, you have the read sensor state. If you're in idle, you finish. You go to read sensor, you finish, go to idle. And then in idle, if you receive CAN packet that tells you to send data, so the data go back to idle, keep going. So that's one way you'd like start planning out your code. You could also be able to just pseudocoding like your case of like case idle, if this do that, and then case sensors if this do that, and then you implement the code.
Now we can do something fun. This board actually has a small LED here, and it has RGB. So, gamers, yeah. So we're gonna try to configure that RGB LED. and let it like cycle through some colors. So looking at the board, you could also look at a schematic for the board, like Googling. But just looking at this board, I don't know if you guys can see that, but right here, it says 5.2 R, 5.3 G, 5.4 B. That's because the LED has 3 pins for the 3 colors, RGB, red, green, blue, right? And those, let me focus here. And those numbers correspond to the pins on the board that you want to assign. So heading back over to top design. All right, Davis, do we want to have them test UART before we do this?
I think just test everything at the end. Like if you want to try, we can run through the debugging process of someone.
Sure.
Actually, that'd be a great thing to do. Bring someone lucky volunteer to the front. We'll debug it.
All right. Okay. All right. So head over to top design, and we're gonna add 3 pins to represent the 3 LEDs. Okay. So search pin in the top right. And down here, you're gonna see digital output pin. All right, let's just drag one here for now. I'm gonna name this pin LEDR, all caps, represent the red LED. Yeah, we're gonna keep it on digital output. Yeah, all of these default settings are fine. So you can just click apply, okay. And if you want, you can hit Control C, Control B. And then you can rename the other 2. LED G for the green one. LED B for the blue one. And how RGB works, you might have stumbled across it, but usually you see like 3 parameters, like 0, 255, 255, or like say like 25500 would be red because red has the highest value. And the ratio of these values will they're like additive, and it'll be like the resulting color, right? So say red and blue would be like violet, right? So then you'd be 255, 255. It doesn't have to be 255. In this case, 255 would be like a brightness. So that would be really bright. But it's the ratio that matters for color, not the brightness, right? So you could do 100, 100, 0, 100, it'd still be violet, just be dimmer. Right. And for brightness, because these are digital outputs, and when you say digital, you just think of 1 and 0s. There isn't like a medium or like a range, just 1 and 0, on or off. So we need a way of having brightness where only information is on or off, right? So what we can do is, if we blink an LED really, really fast, so it's on here and like off down here, like blink it really fast, faster than the human eye can perceive. These gaps we will perceive as being dimmer. So the LED will look dimmer, but it won't actually like be dimmer. It's just blinking really fast. So to do that, we're gonna add a PWM block, which will generate that square wave on off, on off, on off. So go back to top design, and we're gonna add PWM. So search PWM, and you're gonna find the very first option, PC PWM mode. You just want to drag that over. And we do need 3 because we want to generate different square waves for 3 of them, so that we can configure like different ratios and make different colors. Yeah. I'm gonna name this PWM red. All right. Go ahead and double click the PWM red, and then go to the PWM tab. We're not going to be using interrupts for this, so you can uncheck interrupts. It doesn't really matter, I think, but just uncheck it. And what this is gonna do is it's gonna count up really fast, right? Depending on the clock. It has like a counter, it'll count up to some value. Right now it's 65,535. And then it'll drop back down to 0. It's just gonna keep doing that, right? And that's how it's gonna generate the wave. But you can set like a compare buffer to some value like 30,000. And then it would count up to 30,000 and reset and then be low for the amount of time that it lost, basically. And then you'll have the square wave. I hope that made sense. It's kind of, yeah, anyway. We're actually gonna set the period to 255 instead of 65,000. Just because it's a RGB and RGB values we do 0 to 255. So it's just looks nicer that way and it makes sense. And the compare buffer, doesn't matter because we're gonna rewrite it, but you can just set it to 0 to start. And that's just 0% duty cycle, always low. Also, I don't really know why, but we actually want an inverse output. For some reason, the RGB LEDs work that way. When I had,
It could just be the way that they're wired.
Yeah.
Like whether it's anode or cathode.
yeah, so usually you would have this guy on top, but we're inverting it. Because that's just how the LEDs work for some reason. Yeah. So yeah, this is important. Make sure you have inverse output. This guy can say the same. We aren't actually using that. It is 255 and 0. Everything else is fine. Hit OK. Now I'm gonna make 2 copies of this. This is great. Okay. And go ahead and name them accordingly. I'm gonna name this one green. PWM green. This one's gonna be blue. Now let's hook them up to the respective LEDs. To do that, on your keyboard, you're gonna hit W. You can like drag them to a nice place first. Hit W, hover over this connection right here, and then drag it over to line and click. Well, you don't have to drag, just click once and then click again. And then hit W again for the other ones. And 2 clicks.
So how do you do the wiring?
Hit W and then click on the terminals, the little squares. All right, we need a clock to control our PWM blocks. Sorry. So once you're ready, on the right side, search clock. And drag over the one labeled clock. Like somewhere on the left.
Or more and
Clock. It's just called clock. Okay, so with the clock, we only need one of them. And you're gonna wire it to the clock terminal on the left of each block. So WW. Sorry. And you're gonna create a junction here. Just with W, click anywhere on here. And then go into the other clock. Make sure you're clicking on the little square so that the crosshairs show. All right, so it should look something like that. The default clock setting should be fine. You can see it's like 12 megahertz. So it's 12 million times a second where it's pulsing. So that's why you can't really tell that the LED is blinking. You just see a difference in brightness. Yeah. If you have all that, head over to the pins tab. Is everyone caught up? Yeah. Okay, head over to pins. And you can see there's 3 new ones because we added 3 new pins. Let me make sure. Okay, in order of RGB, we're gonna have 5.2, 5.3, 5.4. So starting with R, you're gonna find 5.2. Oh, that's not in order. Nice. 5.2 is up here. And then G should be 5.3. 5.3 is yellow and it's down here. Then blue should be 5.4, which is up here. It's green.
Yeah,
Okay.
just do it.
Alexa, turn Dominic down. Let me look back at the data sheet. This is a data sheet for the PWM blocks, like the bigger ones. And the API, you can see that to initialize it, it's also underscore start. So just replace TC PWM with whatever we named it, which was like PWM red, green, blue, right? So head back to main.c. You'll get a red squiggly line if you haven't hit build yet, but you can ignore it for now because we're gonna hit build later anyway. So let's do PWM red start. Right. And have this before your for loop, but still in main. Right. We need 3 of them because there's 3 blocks. So you want a red start, a green start, and a blue start. And if you remember the top design, I talked about a compare buffer, which is a value it's going to come up to before resetting in each clock cycle. So basically in one clock cycle, it'll count up to 255 and reset. But if you set a compare buffer, it'll count up to say 100. We set a compare of 100, then it'll reset, and then it'll be nothing for the rest of that clock duration. And then in the next cycle, it'll count up again. So that's why you have this low state for whatever amount of time is left. So you'd have 155 units where it'd be low. Yeah. So to change that compare, because we want to change like the ratio of it being on when we're changing colors, we're going to use another API function. If you look in here, there's a function called write compare, and you're just changing what's in the compare buffer. So changing what's going to reset it. Obviously, if you put it over 255, it's not going to make a lot of sense. So keep it between 0 and 255. Yeah. So let's start with red. Red underscore write compare. Yeah. 255 is actually pretty bright. So I'm gonna say like 200. Now I'll just hit build for now. All right. Now over here you can see the red LED is on. Yeah. So in the same way you can configure the other ones. So if we wanted to show all 3 colors in a small cycle, we can do something with the same side delay command from earlier. So I'm gonna set blue to 0 at the start. And you can kind of just think of these as like RGB values. So I set them from 0 to 255. So that means blue is going to be nothing. And then I'm going to set, after the first delay, I'm going to set green to 200. And at the same time, I'm going to set red to 0. Right. You just copy and paste all these. And then the next delay, let's set green to 0. I'll like section these out. So blue 0, red on, delay. Red off, green on, delay. And then lastly, green off, blue on. You can comment out the UART thing, or you can leave it there. It doesn't really matter. Blue on, delay. And then you can hit build again. And I'll come back to this code, but you can see that it's red, blue, green. Yeah. I just added another line to make violet. Or is red and blue violet or purple?
Same thing.
Is it the same thing?
I mean, you're not like certifying yet.
I'll see if the violet works. I'm just keeping red and blue on with green off. Yeah. So it's red, green, blue, violet, red, green, blue, violet. Yeah. And if you have a for loop that like decrements over like a little delay, like you decrement one, increment another, it's probably some formula to cycle through every RGB color. You can make it like a nice. I didn't go through like trying to make that work though, but yeah, you can figure that out. All right, who wants to volunteer their laptop?
You want to explain?
Oh, explain what? Oh, so if you didn't eavesdrop on Davis earlier, we're gonna debug one of your laptops, or not your laptop, but your program on your laptop by connecting it, and we need a volunteer.
After.
Yeah. Okay. Yeah, you can come up here. Should we connect the HDMI to show everyone, or?
Yeah, go for it. I think we should also end the.
I don't think this one has
This is
anything
kind of the
left.
tutorial. It's just like.
Okay. Sorry, 1 second.
So if you go to stop, stop recording.
Oh,